Hello everybody and welcome to the second video on apportionment. So we left off here with me showing you 4 methods, 3 real methods, and now we're going to move on to how do you visualize these methods. This visualization will be key to how we analyze these methods with calculus when we get there. So the geometry of apportionment, how does this work? How do you visualize an apportionment method? So it's worth pointing out that visualizing things is of use. So just like how looking at the graph of y equals x squared sort of shows you visually how that function behaves, an apportionment method also has a visualization that can just show you graphically how the method is working. So we end these slides today by discussing how a method like Hamilton's method can be seen. And we focus on the case n equals 3 for reasons that will become clear. So let's start with thinking about geometry of this. So when n equals 3, there are 3 candidates. There's candidate 1, candidate 2, candidate 3 in that order. Their quotas add up to the delegate total. Okay, so we've seen that, right, in previous examples. D here is a fixed constant because D is being divided amongst the 3 candidates. So this quota, my fair share plus your fair share plus the other person's fair share, that carves up what's available. You've carved the pie into 3 pieces. And D here, it's worth pointing out again, is fixed. So you're fixing D at 8 delegates or 15 delegates or whatever. So D is fixed, but these quotas can vary depending on how the election shook out, you know. So if candidate 3 does terribly, then Q3 will be very small. But if candidate 3 does a little better, Q3 can go up some. So let's just start by thinking about this equation here. What kind of geometric object is this equation? Keeping in mind that what's varying here, what's changing, are Q1, Q2, and Q3, but D is fixed. So if we were in class, we would of course discuss this, right? But notice, if you have 3 variables adding to a constant, so imagine there's an 8 right there. You have variable plus variable plus variable is 8. If you were to label these variables with different letters, like say use an X there, a Y there, a Z there, it then becomes clearer what kind of geometric object this is. X plus Y plus Z equals constant is a plane. So let me just show you that real quick. So X plus Y plus Z, let's say there are 8 delegates. Okay, so here's the plane. Zoom out. There it is, okay? Now the thing about this plane is it's a little deceptive to draw the entire plane, okay? Because these quotas here, so Q1 is my fair share, the amount of delegates I am owed. And then Q2 is your share, candidate 2, the amount you're owed. Quotas cannot be negative. It would make no sense to say that I am owed -3 delegates. So you do get a plane, but you have a domain restriction. All 3 of these things have to be 0 or bigger, which puts you over here in the first octant. So what you get is like a triangle. You get an equilateral triangle where you go up here, down there, and then over. Okay, so you get a line here on the floor, and then up to that point and down to that point. You get an equilateral triangle filled in that's slanted in 3 space. That's what kind of object you get. And let me show it to you. I mean, here it is. This picture, of course, is sitting on a 2-dimensional screen, so it's not, you're not thinking of it as living in 3 space necessarily right now. But that's what it looks like. So 0, 0, 8, that's on the z-axis right there. 8, 0, 0, that's on the x-axis. And 0, 8, 0 is on the y-axis. So let's see, do I have this oriented properly? Let's see. Okay, so this is the x-axis, y-axis, z-axis. So right here is 0, 0, 8. Here is 8, 0, 0, and 0, 8, 0. Okay, so first, I just want to make sure we're comfortable with navigating around this triangle. So these are the integer points, right? The whole number points. These triples here are the possible apportionments because apportionments must consist of whole numbers. So it's possible, right, that candidate 1 gets 6 delegates, candidate 2, 1 delegate, candidate 3, 1 delegate. So as you fill in the rest of the triangle, you're filling it in with triples that aren't necessarily integers, right? They have decimals as part of them. So let me just show you how you navigate the triangle. So you'll notice that if you just draw a horizontal line, like here's one, the third coordinate is always the same across any horizontal line. So across this horizontal line, candidate 3's quota is 2. So this dashed line here is a visualization of candidate 3's quota being 2. And down here, see the 1, the 1, the 1. So candidate 3's quota here is 1 everywhere. Now there's some decimals in between involving candidates 1 and 2, but candidate 3 is fixed here at 1. And then halfway between those two dashed lines is this dashed line here, consisting of where candidate 3's quota is 1.5. And here's where candidate 3's quota is 0.5. So if I were to tell you, like, hey, visualize for me in this picture, where is Q3, let's say 2.3 or something. Where is Q3 2.3? So you'd say, well, here it's 2. So 2.3 is just a little higher. So you draw a horizontal line along this. Something like this is where candidate 3 is 2.3. Up here would be like, 5.8 if you're right here. Q3 being 5.8. So all that to say, a horizontal line in this picture corresponds to holding candidate 3's quota constant. And the higher you put that line, the higher candidate 3's quota is, till you get to the very top of the triangle where candidate 3's quota is 8. This is sort of candidate 3's triangle, or vertex up here, where candidate 3 gets all the delegates. And the other candidates get nothing. Okay, so you can do the same thing with candidate 1 and candidate 2. You just kind of have to tilt your head a little bit. So here's candidate 2's corner down here, where candidate 2 gets everything and everybody else gets nothing. So candidate 3's lines, where quota 3 was held constant, were horizontal. They were parallel to the floor. Okay, but from candidate 2's perspective, what is the floor? It's this edge over here. So if you're going to keep Q2 constant, you're going to draw these slant lines right here that are parallel to this edge over here. This is candidate 2's floor, where candidate 2 gets nothing. Right? That's bad for candidate 2. So here's Q2 equals 0.5. It's between where candidate 2 gets 0 and where candidate 2 gets 1. See, candidate 2 gets 1, 1, 1, all that way. This line here, Q2 equals 1, you can see the 1's in the middle, right? 1, 1, 1, so on. And then here's Q2 equals 1.5, Q2 equals 2, and so on. This line here would be Q2 equals 4.5, and so on. So if you're going to hold candidate 2's quota constant, you get these slant lines that are, again, they're horizontal from candidate 2's perspective. Because again, candidate 2's floor is this. So they're not, of course, actually horizontal, but in the same way these are horizontal from candidate 3's view up here, these lines are horizontal from candidate 2's view down here in the bottom right. And similarly for candidate 1. There's one edge of the triangle left we haven't thought about. If you draw lines that are parallel to that, that's where Q1 would be held constant. Yes, Q1. I'm so sorry. This should say Q1. Right? We just did Q2. Sorry, that's a typo. These are Q1s here. Sorry. So Q1. These aren't uploaded to Moodle yet, but I'll fix that before I upload it to Moodle. Anyway, so along this line, Q1 is 0.5. Q1 is 1. See all the 1's in the first coordinate, right? Those are being held the same. So as you move along this line, you're not changing what candidate 1 is owed. And, again, right, from candidate 1's perspective down here, these are sort of horizontal lines. They're parallel to candidate 1's floor, where she gets nothing, right? Zeros all the way down the line. Okay, so if I give you a given point, like this one, like where is 1.4, 3.9, 2.7? The way you could figure out where that is you could go to height 2.7. So here's Q3 equals 2.7, like this, right, horizontally. Then go to, I don't know, pick your favorite other candidate. Let's think about candidate 1 getting 1.4. So candidate 1 gets 0 here, gets 1 here. So then you're going a little bit past that. Right, so this line's maybe not quite exactly in the right spot, but you get the idea. So 1.4 for candidate 1 is between where she gets 1 and 2. And then where does candidate 2 get 3.9? Well, here's where she gets 4, right? 4, 4, 4. So you back off of that a little bit, and you get a line like this. And where do those three lines meet? They meet at this point. So if I give you a point, you can sort of locate it by drawing the three lines. I mean, you only need 2 lines, of course, right? So you could have omitted the Q1 line. You get an intersection of 2 lines. But all 3 lines will sync up at the same spot. So that's how you locate a given point. This now, right, this could represent quotas. So candidate 1 could get 1.4, candidate 2, 3.9, candidate 3, 2.7. And then where would that visually be inside this triangle? It would be right here. That's how you would visualize a given list of quotas. So if you calculate 3 quotas, that point has to live somewhere in this triangle. You locate it like this. Okay, finally, that triangle needs to be carved into regions where all of the points in the same region flow to the same integer point. So again, way back up here, right? 3, 2, 3. That's a possible apportionment. There will be some quota points that go there. So think about, I don't know, 2.9. So 2.9, 2.1, what's left? 3, right? 2.9, 2.13. Hamilton's method would send that to 3, 2, 3. So basically, if you leave this point a little bit, you jiggle yourself off this point a little bit, you'll be forced to flow to 3, 2, 3. This point here, 1.4, 3.9, 2.7. So Hamilton would round down, so 1, 3, 2. So that's a total of 6. So there are 2 left over. So this would get boosted to a 4. This gets boosted to a 3. So 1, 4, 3 is the point. This point here would flow to this integer point right here. Okay, so you can take that triangle and carve things up into regions where all the points in the same region flow to the same integer point, and that's how we'll visualize these methods. So here is a picture of Hamilton's method with 8 delegates and 3 candidates. So everything inside this hexagon right here, these are all quota points that would get mapped to 5, 2, 1. The Hamilton apportionment would be 5, 2, 1. And everything in here, everything in this hexagon right here, all these quota points would flow to 2, 2, 4. So again, things that live in here are things like 1.9, 1.7, 4. What's left? 4.6 or something. 1.9, 1.7, 4.6. That would flow to this point. So that's like somewhere up here, I guess. Somewhere up in the upper regions of this hexagon. So Alexander Hamilton didn't know it, but again, I'm sure they cover this in his musical. When he proposed his method of apportionment, he was proposing a hexagonal tiling of an equilateral triangle if there were only 3 states. There were, of course, 13 states, and there may even have been 15 by the time they were doing this, right? So this diagram doesn't apply to that. You would need a diagram with integer points consisting of 15 coordinates. So you'd actually be living in 15 space, okay? So you'd be tiling a 15-space tetrahedron with 15-dimensional analogs of hexagons. That's what Alexander Hamilton was proposing. It's not quite how he phrased it, of course. But anyway, this is a picture of Hamilton's method. This is nice. Okay, so before I show the other two, let me just point out that with 3 candidates, there are 6 possible ways you could order them. So candidate 1 could be in the lead, followed by candidate 2, followed by candidate 3. Candidate 2 could be in the lead, followed by 1 by 3, and so on. So since there are 6 possible orderings of the candidates, those 6 possible orderings carve that triangle into 6 regions, corresponding to the 6 orderings. And it turns out that any one region is a reflection of any other one. So like this right triangle right here, this 1 over 2 over 3, it's going to look the same as 1, 3, 2, but you're going to reflect over this line right here. So this line represents where candidates 2 and 3 are tied. Because notice when you hop over it, suddenly candidate 3 is ahead of candidate 2. Candidate 1 is still in the lead though, you know. So this bottom third here, this bottom third is where candidate 1's in the lead. When you cross over this line, candidate 3 is now moved into second. And similarly for all the other ones. So in this region here, 2 is over 3 is over 1. Here 2 is over 1 over 3. These two regions are just reflections of each other. So you can see that in this picture. So if I were to carve this up, so I do like that, and like that, like that, and so on, right? So down here, in this bottom 6th right here, I just get this hexagonal tiling, and then I could sort of reflect it around to fill in the rest of this diagram. So everything is symmetric by candidate ordering, okay? And that makes sense. No candidate gets treated any better or worse than any other here. Okay, so here's a picture of nearest integer extremes. This is with 12 candidates. I chose a bigger candidate number just to give you more perspective on what's happening here. And notice, this is nice. Look at this picture. So here there are 12 delegates at stake as opposed to 8. So if you were to look at the triples here, they'd have to add up to 8. This is what NIE looks like. So down here, let's focus our attention on the bottom 6th. So down here in the bottom left 6th, that is where candidate 1 is over candidate 2 is over candidate 3. And notice what these apportionment regions look like. They look like little arrows pointing down and to the left. It makes sense they're pointing down to the left because they're sort of trying to point towards this point down here. This is candidate 1's point. So you can see kind of the bias. These regions are stretching down. They're stretching away from candidate 3. When you're down here, candidate 3 is in last place. So moving away from him corresponds to the punishment that candidate receives. Okay, so this method is not proposing a tiling by hexagons. It's proposing a tiling by these arrow-shaped things, but they get reflected around. So like this arrow down here becomes this arrow over here when you reflect it up. So this picture is symmetric, but it's not hypersymmetric like this is, right? Like you get hexagon here, the shapes don't change. The reason the shapes change here as you move around through the diagram is because the ordering of the candidates change, and this method cares very much what the ordering of the candidates is, right? If you're in first place, you get a boost. Last place, you get a punishment, perhaps. That's why you're seeing not the hypersymmetry of Hamilton's method. It's still symmetric, right? So this bottom left sixth, if you reflect it over this line right here, you get this region over here. So you still can get things by symmetry by reflecting things around. But again, this bottom right region is not literally the same as this bottom left. They're reflections of each other in the way that like this bottom right region here is literally this. You don't change what the shapes look like. So I guess I should just say, it's not clear why these pictures are true necessarily, right? You take them as a given. So this picture has been known since like the 1970s or something for Hamilton's method. This picture I made was not known until I made this picture. But again, like I just made this. You don't have to worry about where it comes from. Finally, here's what SUQ looks like with 12 delegates. This one's a little harder to read because see this one, the point's in the middle of the region, so you're like, the stuff surrounding that point flows there. Here, the points are actually on the boundaries of the regions. And what's happening here is, see this diamond right here? This diamond is all flowing to this point right here. This point down here. This diamond here, everything's flowing down to this point. And the reason there's downward movement, this little trapezoid here flows down to this point. The reason there's downward movement here is because down here, candidate 3 is in last place. Right, candidate 3 is way up here. There's his corner. Down here, candidate 3 is in last place. And SUQ is designed to punish the last place candidate. It really hurts the last place candidate. So you're seeing like these regions, they're reaching downward. They're trying to scurry away from candidate 3. So this point down here is sucking up all these points from above. And then this point down here in the boundary, it's eating up this sort of sawtooth stuff. This point here gets all the sawtooth stuff here, and so on. So 3 very different pictures. This looks kind of like a snowflake or something, right? SUQ proposes a snowflake. NIE proposes these arrow things, and Hamilton proposes hexagons. So to close out this video, let me just point out, these are hard to read, right? So if you have questions on these, let me know. But so far, these methods, it seems like what they're doing is they're basically deciding on a shape. So Hamilton's like, I like hexagons, so I'm going to tile things with hexagons. NIE is like, I like these arrows, and they're going to point in different directions depending on where you are in the diagram, you know, depending on who's in first and who's in last, but I like these arrow things. That's what I'm going to use. That's my like canonical basic shape. And then SUQ, it's a little harder to see because actually 12 delegates is kind of small, so it's kind of hard to see what's happening, but these diamonds will end up being the canonical shape. So as you can see, when you're at the boundary, things get distorted because you're artificially chopping things off. So Hamilton has these like half hexagons or like a sixth of a hexagon down here. NIE has these half arrows and then a little parallelogram down there. SUQ has these sawtooth things and a triangle down here. But if you were to keep getting bigger and bigger delegate counts, you'd keep making this picture bigger and bigger. All you're going to do is see more and more diamonds. In this case, you'll see more and more of these arrow things. And in Hamilton's case, you just see more and more hexagons. So basically what I'm saying is every method that we're looking at has like a shape. You know, hexagon, arrow thing, diamond. Okay, so that's how we visualize apportionment methods. In the next video, I'm going to talk about bridging over to the calculus. So far, we don't even have a calculus question here, right? So I want to start setting up the calculus question and bridging us to where calculus can tell us things about these methods.